Hello, I'm Wei Cheng from Google. I'm excited to share with you our work, Mask2CAD, which is a joint work with Anelia, Tongyi, and Angela Dai from Technical University of Munich. In the past few years, we have witnessed significant progress in 2D object understanding. From a single image, we can find the bounding boxes and masks of the objects in it. Consider this image. In addition to the boxes and mask, a human can easily see the 3D geometry of the objects and even the invisible parts. Can a computer do this as well? Recently, we have seen tremendous progress in single image 3D shape understanding. Voxel, mesh, point, and implicit functions have all been proposed to generate object geometry from a single image. These approaches are developed on ShapeNet, which is a synthetic dataset with a white background and one object in each image. It's challenging to make the models trained on ShapeNet work well in the real world. In fact, as far as shape representation is concerned, CAD model could be a promising representation itself. It's compact, watertight, aesthetically pleasing, and widely used by artists for content creation. Therefore, we propose to retrieve and align the CAD models to image. Mask2CAD outputs a set of CAD models and their poses as seen on the right. Here's the method overview. Let's delve into each part. We take the ROI feature of each object to predict a shared embedding space between RGB and shape rendering, inspired by light field descriptor. The positive pairs in red come from image annotation, while the negative pairs in green come from the other examples in the same mini batch. We adopt contrastive loss with hard example mining because we observe that contrastive loss tends to be more stable than triplet loss in our case. The summation of distances are over the hard examples only, determined by a temperature-adjusted cosine distance. Hard example mining help our model achieve better performance. From the same ROI feature, we also predict the rotation and translation of the object in the camera space. For rotation, we first perform k-metalid clustering on the quaternions of each class and obtain k-canonical poses. Then we learn a k-way classifier as well as a quaternion regressor from each bin. To avoid dissimilar targets, we only have losses from bins within 30 degrees of the ground truth pose. For translation, we regress the projected 3D box center in blue from the 2D box center in orange. The deltas are normalized by the bounding box size as in the standard bounding box regression. We significantly outperform the state-of-the-art on Pix3D in Mesh AP. Inference time is 60 milliseconds. Notably, we quadruple the performance at AP75. Visualization shows that our reconstructions are clean and accurate. A unique benefit of our CAD representation is the flexibility to add models at test time. This improves the performance for all categories. We compare our system with the state-of-the-art method by using ground truth mounting boxes, which eliminates the effects of object detection. We outperform with a notable margin on f-scores and chamfer distance. To further contextualize our work, we compare our Pix3D trained model with existing ShapeNet models on the chairs of Pix3D testset. The ShapeNet models are trained with real data background augmentation to bridge the sim-to-real gap. Ours outperforms in both IOU and chamfer distance. Here's a t-SNE embedding learned by our model. We can see a clear separation between different kinds of beds here. Here we see similar bookcases grouped together. Same thing here for tables. Finally, we propose a new baseline on ScanNet because the dataset contains more shape, occlusion, view, and lighting condition. It also has inexact CAD model matches, which presents additional challenges. We train the model on Scan2CAD annotations. Even under notable clutter, we can still predict the shapes of many objects accurately. In conclusion, we propose Mask2CAD that performs 3D shape prediction from a single image by retrieval. We achieve new state-of-the-art and can generalize better by adding CAD models at test time. The system runs at 17 frames per second and can compactly digitize real images. Thank you for watching.